Now on Friday you should be wearing red, white, and blue. We're going to have a Veterans Day Assembly. We'll have veterans on the campus. In fact, if you were listening to the announcements, except for people who couldn't hear the announcements because they were already answering, you would know that they've invited any relatives that you have that are veterans. Okay? Yes?
When is it?
Yeah.
What period is it for?
Yeah.
No, second period. All right, please pay attention.
Wait, but they said we're not leaving at RDA.
I don't know what to tell you. I'm just telling you we have a Veterans Day Assembly in second period on Friday. Is that my phone ringing? I have it ringing in my ears or something. Okay. So I gave you this. And then you're supposed to finish everything else. Okay? So I'm looking at this and I see I have an element that's by itself. And I have an element that's like it in the compound. The part that's like it is a halogen. This is a halogen, this is a halogen. Halogens replace halogens in single replacement reactions. Metals replace metals in single replacement reactions. You don't replace metals with halogens, or vice versa. So this chlorine can only replace another halogen. So we put calcium then with chlorine over here, and the bromine ends up by itself. Okay? Now you are supposed to know that bromine is one of these 7 diatomic elements. Okay? Forms a diatomic molecule. So bromine is going to have a subscript 2 because it's diatomic when it's an element by itself. We need to, first of all, I need to know if there's a driving force. Actually, I could have done that before I did anything else. With single replacement reactions, you can determine if a reaction is likely to occur before you predict any products. And to do that, you use the activity series of halogens. If one of these elements is higher than the one in the compound, then the reaction tends to occur. So chlorine is higher, it will replace bromine. Now we're ready to balance the formula. Okay, I'll give you a makeup. It's all right. Okay. So calcium has a 2+ charge. You would know that by looking on the periodic table with the oxidation numbers, or just because it's in column 2. All elements in column 2, all of the alkaline earth metals, those are the ones in column 2 of the periodic table, have a 2+ charge when they're bonded with in an ionic compound. Chlorine has a 1 negative charge. And you would find that on the periodic table with oxidation numbers, or if you just knew that anytime you have a binary compound, elements that are in column 17, also sometimes numbered 7A, all those have a -1 charge in a binary compound. So in order to charge balance this formula, I need 2 negative charges to balance this 2 positive charge. So I need 2 chlorides. And that means I need a subscript 2 on this formula here. All of the diatomic elements, except bromine, are gases. Hydrogen's a gas, nitrogen, oxygen, fluorine, chlorine, and iodine are all considered gases in this class. Okay? All of them are gases except iodine, which has a kind of a strange thing it goes through. But bromine is of those 7 that you're supposed to know about already. Bromine is the only one that tends to be a liquid. Okay? And now we're ready to balance the equation. So we list all of the elements in the atom inventory. We've got chlorine and calcium and bromine. So we have 2 chlorines here, 1 calcium, 2 bromines. Over here on this side, I've got 2 chlorines, 1 calcium, and 2 bromines. So that's balanced already. Okay? So that's the complete equation. Now we're going to write a complete ionic equation. So what we're going to do is we're going to take anything that is ionic and aqueous and break it up into separate ions. And so the only two compounds that are aqueous, actually I didn't give you the physical state of this, let's check that out. Chlorides, it says in the solubility rules, are mostly soluble. So if there's water around, it will be aqueous. Now there are some exceptions, silver, lead, mercury, but that's not silver, lead, or mercury, that's calcium. So then this chloride must be one of those soluble compounds, so if there's water, it must be aqueous. So this is a physical state of aqueous. Okay? Alright, now we're ready to write the complete ionic equation. So chlorine here is not aqueous, it's not ionic, so this chlorine molecule is just going to remain Cl2, a gas. This is ionic, and the way you would know is it's a metal bonded with a nonmetal. Okay, you have to know enough about your periodic table and the regions to know that's a metal bonded with a nonmetal. So is this a metal bonded with a nonmetal? Both of these are ionic compounds. The two ways you can tell when you have an ionic compound are, number one, when you bond a metal with a nonmetal, or number two, when the formula has a polyatomic ion in it. So we're going to break this up then into separate ions. So this is the reverse of the process we learned in Unit 3. We first learned to balance compounds, like I balance these compounds here, by writing out the ions first and then charge balancing it with this coefficient 2. We're undoing that process here. Okay? So calcium has a 2+ charge. We said so here. Since what we did to make this aqueous was to break it up. The way you dissolve an ionic compound is to break it up into separate ions. Well, it's still dissolved in water. The ions are dissolved in water, so the ions are aqueous. And we have 2 bromines. This 2 here is not part of a polyatomic ion. So it's telling me I have 2 bromide ions that are going to separate. Okay? On the other side of the equation, I've got an ionic compound. I've got to break it up. We said calcium's 2+. It's going to be aqueous for the same reason we expressed over here. And I have 2 chloride ions. And chlorines, we said, have a negative charge when they're in a binary compound, or an ionic compound. And then the bromine molecule over here is not ionic. Okay, it's not going to break up or anything, so we're just going to write it exactly like it appears here. And that's your complete ionic equation for this equation. Now we want to write a net ionic equation. In the net ionic equation, you keep those things that change, and you don't write down the things that stay the same. So if you look carefully here, calcium is the only thing that stays the same from the left side of the equation to the right side. Okay, it's a 2+ charge, aqueous on both sides. Chlorine is a molecule over here, and over here is an ion, actually 2 ions. Bromine is a molecule over here, and over here is 2 ions. So it's 2 separate things. The chlorine and the bromine we keep in the net ionic equation. And that's the net ionic equation. Alright, so let's look at how we're going to go about grading this. Since you had to put calcium and chlorine together, those are worth each a point. That's 2 points right there. The subscript 2 is necessary to balance the formula. That's worth a point. And the physical state is worth a point. The fact that you wrote bromine with the subscript 2 and the physical state, those are all worth points. And by the way, down here it tells you it's going to be in a single replacement reaction, bromine by itself is going to be diatomic. So that's kind of a help right there. That's 4 of the 7 diatomic elements right there. The other 3, hydrogen, oxygen, and nitrogen, you just have to know about. I mean, you should know about these, but you could look them up. Yes, it is. Yes, it is, but it's not written in. It's written H2 here, isn't it? Okay, so hydrogen by itself is H2, so by golly, you only know 2 of them, do you? Right? All right, that's good. So that's 7 points there. Each of the elements you list in your activity, your atom inventory are worth a point, and the counting them are all worth points, so there's another 9 points. The fact that you wrote chlorine, the symbol, and the subscript 2, and the gas physical state, those are all worth points. Calcium symbol, charge, and physical state is worth a point. The coefficient in front of the bromide ion, its symbol, charge, and the physical state symbols are all worth points. Calcium, charge, physical state, coefficient, chlorine, charge, physical state, bromine, and the fact that it's a liquid is worth a point. Okay? You just brought that down here, so I'm not going to give you a point again for the subscript. Okay? So in the net ionic equation, all you did was to take this whole thing and drop it down here, so that's worth a point. I'm going to give you 2 points for this one because it's important that you have the coefficient there. One point is for the coefficient, the other is for the rest of the ion symbol. The same here, coefficient, ion symbol, and then that's for the whole Br2 liquid. Okay? So that's worth a total, the whole thing is worth a total of 40 points. And those aren't percentage points, those are just points. Okay? Alright, so this is the next equation you're supposed to do. If you're still grading this first one, raise your hand. Let me know to wait on you. Okay? What? Is it 41? Well, we'll give you an extra point then, okay? So we're going to call it 40. I got miscounted something. Alright, so here I have what is an acid, but when we're figuring out the products, you're going to treat it like it's an ionic compound because you're going to exchange the front part and some back part. So this is treated like an ionic compound. In fact, it is. Acids can be both ionic and covalent. And this is ionic because it's a metal body with a nonmetal. So this still is going to be a double replacement reaction, okay? The front part of this goes with the back part of this, front part of this with the back part of that. But you don't carry over subscripts unless they're part of a polyatomic ion. And that's the only subscript, that 4 right there, is the only subscript that's part of a polyatomic ion. So it's the only one that carries over automatically. For this, we're just going to take this H here and put it with this Cl. And we're going to take this Sr and put it with this SO4. And now we're going to determine physical states so we can see if we have a driving force or not. Now with single replacement reactions, the driving force was the fact that chlorine was more active than bromine. And we knew that because it's higher on the activity series than bromine. With double replacement reactions, there's a different set of driving forces, plural. One is the formation of a gas. You can know that, but we're not going to do any problems where gases are formed in this class anyway. So the other two driving forces, the formation of water, and there's no water formed over here, or the formation of a solid. Now to figure out if we have a solid, we've got to use those solubility rules again. So let's look at the first one here. So chlorides, it says down here, are mostly soluble. There are some exceptions, silver, lead, and mercury chlorides, but this is hydrogen chloride, or hydrochloric acid. So that's not an exception. So this chloride must be soluble if there's water around. An aqueous here and here tells us there's water around. If there's water around, a soluble compound will be aqueous. So we're going to go ahead and call this aqueous. Sulfate. Sulfates are listed here. And it says here that most sulfates are soluble. But wait a minute. Not when they're bonded with strontium. And there's strontium. Strontium is one of 1, 2, 3, 4, 5, 6 exceptions for the sulfate. Okay? So strontium sulfate, most sulfates are aqueous, or soluble, and will be aqueous as there's water. But strontium sulfate is not, and sort of the opposite, if you want to call it that, of aqueous is solid. It's not really opposite, but You know, if it's not aqueous, it's got to be solid.
So this is, yeah.
Okay? Now we're ready to balance the formulas. We do have a driving force. We formed a solid. That's one of the three driving forces in a single replacement reaction. So we want to balance it. So hydrogen has a 1 plus charge. Hydrogens in acids always have a 1 plus charge. Okay? You should just know that by now. Chloride, we said up here, in our previous problem was a 1 negative. Well, if I have a 1 plus charge particle and a 1 negative charge particle, that's already charge balanced. I don't have to worry about anything else. Okay, it's balanced. Strontium has a 2 plus charge. You look on the periodic table that I give you, in this class anyway, it has all the oxidation numbers. You see strontium has only one kind of oxidation number, 2 plus. In fact, every element in column 2, the alkaline earth metals, all have a 2 plus charge when they're bonded in a compound. Okay? So it has a 2 plus charge. So this sulfate here, we've got to figure out what its charge is. And if you look over here in the common ions list, sulfate has a 2 negative charge right there above my thumb. Okay, so yeah, it's already balanced. You're correct. Okay, so we're lucky there. Made it a little easy. Don't have to worry about oxygen. Oxygen is taken care of in the sulfate ion. Listen, if you have more than 2 elements, and this compound over here has more than 2 elements, the first thing you want to do, if you don't know already that's a sulfate ion, is you want to go to this common ions list and see if you can find some part of this formula that looks like something in this common ions list. And if you look close enough, you'll find that sulfate's down here. It's SO4, and that's SO4 right there. So that tells you right there you've got a polyatomic ion in that formula. Okay? Anytime, we mentioned this in Unit 3, anytime you have more than 2 elements in a formula, if you have something other than, say, a hydrocarbon or something, you're going to go looking and see if you have a polyatomic ion using the common ions list as your reference. Okay? And figure out if you have a sulfate. Then sulfate, because the polyatomic ion stays together, tends to stay together. One of the properties of polyatomic ions is they tend to stay together in a reaction, especially an aqueous reaction. Okay? All right. So now that we have our formulas balanced, we're ready to balance the equation. Remember, once the formulas are balanced, we have to leave them alone. You can't change the formulas once the formulas are balanced. So when we balance the equation, we only put coefficients in front of the formulas. No, we don't mess with the formulas themselves. So we're going to list all of our elements. We have a hydrogen here, sulfur, oxygen, strontium, and chlorine. I'll make this grid so we can keep our atom inventory nice and neat. The only reason that neatness counts in chemistry is because it helps you do it right. If you get everything all confused, you can't figure things out for yourself, much less me figuring it out. You have a question? No? You had your hand open like that. You were ready to ask that question. All right. So we have 2 hydrogens here, 1 sulfur, 4 oxygens, 1 strontium, and 2 chlorines. Over here, I've got 1 hydrogen, 1 sulfur, I've got 4 oxygens, 1 strontium, and 1 chlorine. What? Oh, gracious, help me. Okay, you're right. It should be 1 strontium, not the symbol strontium. For some reason, I've been doing that a lot this year. I don't understand why I did it, but I did it. So 1 strontium. All right. So I'm looking through here, and I can see that hydrogen and chlorine are not balanced. Everything else is balanced. But we want to save hydrogen for next to last. Oxygen's always saved for last, hydrogen next to last. So we want to actually balance the chlorine first. To get 2 chlorines on the right, I put a coefficient 2 in front of the species that contains the chlorine. Well, it turns out that's going to change the number of hydrogens and chlorines. Now I have 2 hydrogens and 2 chlorines and the equation's balanced. Okay? All right, so now we're ready to write a complete ionic equation. So look here, and this is a sulfate polyatomic ion. Okay, there's the sulfate there. So what I've attached to that sulfate ion are two hydrogen ions, and hydrogen ions in an acid are always going to be 1 plus. So that means I have two hydrogen ions here. The way that we dissolved this was to get it to break up into all of its ions. So the ions are dissolved, and that means this ion is aqueous. The sulfate ion, I just have one of those. And we said that was too negative over here. And since what we did to dissolve it was to break it up, so the ions are dissolved. Really, the ions are more dissolved than the formula is. I suppose that's kind of a strange way to say it, but that's one way to think about it. Over here we have a metal and a non-metal. It's aqueous, so this is going to split up too. Ionic compounds that are aqueous break up in an ionic equation. So strontium, we said, has a 2 plus charge. Chlorine has a 1 negative charge, and I have two of those. All right, I have one hydrogen and one chlorine in this HCl, but I've got two of the HCl's, which means I have two hydrogens and two chlorines in the complete ionic equation. Now this is ionic, but it's not aqueous, so it doesn't break up. We just drop that down exactly the way it appears there. And that's the complete ionic equation. For the net ionic equation, we're simply going to keep those things that change. If they don't change, we don't keep them. Okay? Hydrogen is exactly the same on both sides. We're not going to keep it. Sulfate changes. It goes from being an ion over here that's aqueous to bonded into a compound that's a solid. So we're going to keep sulfate. Strontium is an ion here, and over here it's not an ion. Over here it's aqueous, here it's a solid. So we're going to keep that. It changes. Chlorine, or the chloride, is exactly the same on both sides. So we're not going to keep it. We're going to leave it alone. Those are spectator ions. Things that stay exactly the same are spectator ions. So over here, hydrogen, chlorine, and spectator ions, we're not going to write those. Only the strontium sulfate solid do we write over on this side. And so that's your net ionic equation. Alright, so this is worth, each of those parts are worth a point. The coefficient, the symbol for H, the symbol Cl, and the physical state. Strontium is worth a point. Sulfate, the whole sulfate is worth a point, and its physical state. Each of the elements here, 1, 2, 3, 4, 5, are worth a point. Counting of them is worth a point. Counting and canceling and the new count are all worth points. So that's 1, 2, 3 points right there. Each of these worth a point. 1, 2, and 3. All right, down here in the complete ionic equation, coefficient, symbol, charge, physical state's worth a point. Coefficient, symbol, charge, physical state. We're going to give the whole strontium sulfate 1 point because it was written up here already. You just dropped it down, and the physical state is worth, I'm going to give a point. All right, that's important that you keep it there. Then the sulfate here is just kept, so I'm not going to give new points for all the parts of it, just the fact that you put sulfate down there, and strontium sulfate here. Okay? So we'll give that a total of 53 points. Any questions about that? All right. I'll finish grading it. We'll start the next problem here in the meantime. Let's see, I need to start on this sheet of paper, really. Might take more room than I've got there. Continued is sort of short. I've shorthanded it. Continued. Yeah. Can't is kind of a dirty word in here.
Really?
Really, kind of.
I didn't mean to say it.
Oh, that's okay. It's kind of a joke in this sense. 99% of the time, students who say they can't do something are really not saying they can't because everybody can. They don't want to is the main thing. And so if you say I can't, basically you've given up. Because I give you lots and lots of chances to get it done, and I help you, and you help each other. You can do it. Like the old Nike commercial. Just do it. Okay? You got to keep working at it till you get it done. Huh? The old Nike commercial. Yeah. Yeah, go Bo, or whatever it was, yeah. Anyway. Alright, so let's go back to this. Who's still working to grade this? Raise your hand if you're still working to grade that. Alright, I'll move out of the way then. Alright, so we have two ionic compounds. This is a metal bonded with a nonmetal, and a metal bonded with a nonmetal, so those are two ionic compounds. If a reaction occurs, it's going to be double replacement. To figure out if there's a driving force, I've first got to put together products to see if I have a solid or water. So I'll put the sodium with the chlorine, put the iron with the sulfur or sulfide. Okay, and now we want to know if we have any kind of a solid form, because there's no water here. Water would be a driving force. We formed water, but there's no water form. So we have to figure out if we're going to have a solid form. So we looked a little bit ago at the solubility rules for chlorine, and it said that all chlorines, with some exceptions, are soluble, but there's no exception for sodium. So sodium chlorine must be soluble. Sodium chloride must be soluble. And since there's water around, that means it's going to be aqueous. Sulfides are down here in the insoluble section. It says sulfides are soluble, except group 1. Now that's column 1 of the periodic table. Iron's not there. Iron is found in the transition metals. Group 1, group 2 is not in group 2 either. That's not part of the transition metals. And it says aluminum is another exception. Well, it's not aluminum. So then this, since most sulfides are insoluble, and there's no exception for iron sulfide, this must be solid. There's our driving force. Now notice I said iron sulfide. Iron has two different oxidation numbers. We just don't yet know what the oxidation number is for this iron. Okay, we got to figure it out. So to balance the formula for this, I'm going to have to figure out what the charge is for iron over here. Now let's go do sodium chloride first. Sodium is an alkali metal. It's in the first column of the periodic table. All of those have a 1+ charge. Chlorine, we said on one of the previous problems, has a 1 negative charge. So that's balanced. Okay? So iron, we don't yet know whether this is going to be iron 2 or iron 3. Okay? Let's look for a minute on the periodic table with oxidation numbers. And it tells you that iron has two different oxidation numbers, 3+ and 2+. All right? So we've got to figure out what its charge is going to be. Now, sulfur, on the other hand, in a binary compound, when it's bonded with something that's positive, has to have a 2 negative charge. So sulfide is 2 negative. The way we figure out what the charge is on iron is to figure out what it was over on this side. Chlorine, we said, had a 1 negative charge, and we have 2 chlorines. So we're putting that together with the 1 iron. What charge does the iron have to have 2 plus. So that makes this 2 plus, and 2 plus and 2 negative, that's balanced. Does that make sense to everybody? All right.
When it says balance, it means neutral.
Yeah, the charge is neutral. That's how you balance a compound, is you get the charge to be neutral. Okay? Unless you're trying to balance something that we don't really deal with a lot in here. All right, there are some ions you have to balance sometimes. We don't really get into that a lot in CP chemistry. All right. So now that we've got all the formulas balanced, we're ready to balance the equation. So we write out all of our elements: Na, S, sodium and sulfur. Fe is iron, and chlorine is Cl. Make our grid to keep everything nice and neat so we can get a good result, get all the math right, and start counting. I have 2 sodiums, 1 sulfur, 1 iron, and 2 chlorines. Over on this side, I've got 1 sodium, 1 sulfur, 1 iron, and 1 chlorine. So I want to get the sodiums and chlorines balanced. To do that, I'll put a coefficient 2 in front of sodium chloride here. That's going to change the number of sodiums and chlorines in my atom inventory so that now I have 2 sodiums and 2 chlorines. That coefficient 2 in front multiplies the number of atoms in the whole formula. So the equation is now balanced. Ready to write the complete Ionic equation. I have 2 sodium ions here. We said sodiums have a 1 plus charge. The way that you dissolve an ionic compound is to break it into its separate ions. And they break up in the solution. So if the compound's aqueous, those ions are also aqueous. So the sulfur is also going to be aqueous. The sulfur ion, sulfide ion, is aqueous. Iron, or iron 2 here, and we know it's iron 2, it's aqueous because the compound is aqueous. And we've got 2 chloride ions that are aqueous. On the other side over here, I had 1 sodium and 1 chlorine in the formula, but when I put a 2 outside, that's 2 of the whole thing. So it gives me 2 sodiums and 2 chlorines down here. And the iron 2 sulfide doesn't break up. It's ionic, but it doesn't break up because it's a solid. So we just simply write it the way it appears here. Okay, and that's the complete Ionic equation. For the net Ionic equation, we write only those things that change. Sodium is here, sodium ion here. They're exactly the same, so we're not going to keep that. Sulfur here is an ion that's aqueous, and over here it's part of a solid compound that's solid. So that's a change. We're going to keep the sulfur or sulfide ion. No. The order you put them in with the plus sign in between doesn't really matter. It matters when you write the compound. But when you write the compound, it matters, not what order you put it in the equation. Okay? So I had to write iron before sulfur over here because iron's positive, sulfur's negative. But when I write it like this, they're separated out. It really doesn't matter what order you write them in the equation. Yes?
So you could change like the iron to plus, like on the left side.
Mm.
You could move the part and move the
Yeah, I could write Fe before S.
You understand? Like not
Yeah.
the
Over here?
Yeah.
No, you can't change this. Iron has to be written before sulfur in a compound.
No, I mean like the SES. Can that go before like two?
Oh, yeah, this could go over here, sure.
Okay,
Yeah. The order of all of this or this doesn't matter. They can be switched around as long as all these are on this side of the equation, all these are on this side of the equation. Okay. All right, and there's your net ionic equation. All right, let's get, how are we going to grade this? Basically the same process we did before. Y'all quit that.
Is it raining outside? I just feel like it's raining. I hope it's raining. Not tonight?
All right, so we have a total of 55 points for this one. And for the whole homework, all three problems, we have 148 points here. Those aren't 148 percentage points. That's 148 points for the homework problem. I'll actually put it in the grade book such that it's weighted the same as something that's 100%. All right, has everybody written these down that wants these? All right, so if you didn't do very well on that last homework, this is what you're going to do for makeup. Okay, I said, well, it's up to you. You don't really have to do it, but. And somebody asked, can I do these for practice? I said, well, of course you can. You know, I'm not going to make you not do it. I mean, it's great practice. All right.
Chemistry changed my life. It made my IQ higher. It also put holes in my clothes and it set my hair on fire. I love going into the lab with that feeling of expectation, knowing soon I will be doing a fractional distillation. And they call me a chemistry nerd, and yes, I'm a true devotee. That's right, I've devoted my life to the study of chemistry. You may carry a snapshot of a sister or a brother. Some keep a locket